Our project aims to design a sustainable floating resort with a floating community in Amsterdam, Netherlands. The selected area is 35,000 square meters in an existing floating community called Waterport. The climate is classified as temperate cold, where in summer the temperature reaches 35 degrees, while in winter it drops down to almost -8 degrees Celsius. The sky cover annual average high is 93%, while the average low is 23%. During the winter, the building's southern facade will be exposed to low-angle solar radiation, while in summer, the solar radiation angle will be higher. As for our selected floating technique, we have chosen the floating pontoon system by using expanded polystyrene. This system has many advantages such as unlimited shape designs, unsinkable, lightweight, easy and quick assembly, cost-effective, long-lasting, and most importantly, environment-friendly. The manufacturing process for this system goes through 6 main phases before the final installation on site. We have managed to formulate the base case design for the floating chalet, which is the key element for the resort design. The selected construction materials are inspired from the local materials which are used in the existing floating community, such as recycled steel for the structure, recycled glass for the glazing, wood from sustainably managed resources. For maximizing the tenant's experience, we've selected an open plan design concept, which allows an easy internal circulation and enhances the visual connectivity between the interior and the exterior areas. The floating chalet consists of hot-dip galvanized steel for the inner structure, followed by an isofoam layer. The facade of the floating chalet will be exposed to wet and damp condition. Therefore, we used Mediterranean cladding. It is waterproof and very stable and FSC certified. By using IES software, we assess the base case against 3 main parameters. The first is natural daylighting, where we found that the average daylight factor is 9.4%. It also showed the glare spots are located around the opening areas. The second parameter is CFD analysis, where we investigated the internal air temperature and velocity. We found that the air temperature average value is 16 degrees Celsius. The third parameter is energy performance, where we calculated the annual heating and cooling load for the base case. The total annual heating load is almost 9 megawatt-hour per annum, while the total annual cooling load is 1.15 megawatt-hour per annum. Most of the annual energy consumption is used for the heating loads between October and May. In order to achieve a sustainable design, we use 3 different building skins. The first proposed strategy is cooling skin by using double skin facade to reduce cooling loads during summer. The second one is a collector skin by introducing sun space within the design to reduce the heating load during winter. The last one is an adaptive skin by integrating a dynamic facade to reduce both the annual heating and cooling load throughout the whole year.
The first scenario for the cooling skin is a box window facade with an uninterrupted space between the glazing surfaces and an air inlet and one air outlet. Scenario 1 showed better daylight performance than the base case in terms of minimum, maximum uniformity and diversity values. By using MacroFlow tool in IES, we identified the airflow performance in Scenario 1. The annual heating loads in Scenario 1 were reduced by 1.93% compared with the base case, where the heating loads were reduced in the period between November and March, and it was increased in both of April and May. As for the annual cooling loads, a significant reduction was achieved by 0.85 megawatt-hour per annum, especially in the period between March and September. Scenario 1 managed to achieve an overall reduction of 10.09% of the total annual cooling and heating loads, despite that the base case performance was better than Scenario 1 in April, but Scenario 1 achieved lower values for the rest of the year. The second scenario is 2 boxes windows facade. which has 2 air inlets and 2 air outlets, divided by a glass partition in the middle. Analysis showed that Scenario 2 daylight performance was slightly less than Scenario 1, but still better than the base case. Macro flow analysis showed that the volume of airflow in and out of the facade was equally divided on each box window facade. The annual heating loads in Scenario 2 was reduced by 1.65% in comparison with the base case. However, Scenario 1 achieved a better reduction with 1.93%. On the other hand, Scenario 2 managed to reduce the annual cooling loads with 0.88 MWh per annum, which is better than both of the base case and also Scenario 1. Scenario 2 reduced the total annual heating and cooling loads with 9.97% than the base case, but Scenario 1 had a better result at 10.09%. The third scenario consists of a 3-boxes window facade with 3 air inlets and 3 air outlets. Daylight performance analysis for Scenario 3 pointed out that it is better than the base case and slightly less than both Scenarios 1 and 2. Macro flow analysis showed also that the same total amount of volume airflow were divided among the openings. Scenario 3 also reduced the heating loads with 1.45% than the base case, but came as the least scenario among the others in the reduction percentage. By contrast, Scenario 3 significantly managed to reduce the cooling loads more than the other scenarios with a 0.9 MWh per annum reduction. As for the reduction in the annual total heating and cooling loads, Scenario 3 achieved a reduction percentage of 9.88%, which is the least among the other scenarios. The results shows that multiple boxes facade reduce cooling loads more than a single box window facade. On the other hand, the multiple boxes facades increase the heating loads. In conclusion, from a cooling load perspective, multiple boxes window facades achieve higher reduction rates than single box window facades. But from a heating load perspective, single box window facades is better, making it the best choice for cold climates.
Moving to the second proposed skin, which is the sun space. The first scenario for this skin is a vertical sun space, which collects the solar radiation to heat the air and transfer this air to internal spaces via 4 openings. Daylight assessment showed great improvement in light penetration since the sided walls were replaced with glazing for the sun space. CFD analysis showed that the average internal air temperature was increased by 2 degrees Celsius, reaching 18 degrees after it was 16 degrees in the base case. The heating loads in Scenario 1 was reduced by 10.56% compared to the base case, where the sun space managed to reduce the heating loads throughout the year. Moreover, the cooling loads were reduced by 0.42 MWh per annum than the base case, especially during the summer period. Finally, the total annual heating and cooling loads were reduced by 13.53%. Scenario 2 has an inclined design for a sun space in order to maximize the solar penetration. This had resulted in higher internal air temperature than both of Scenario 1 and the base case, with 18.3 degrees Celsius value. Scenario 2 had a better daylight performance compared to the base case. However, Scenario 1 showed slightly better performance. The heating loads were reduced even more than both of Scenario 1 and the base case, with a reduction of 10.7% due to the increased solar gain. On the other hand, Scenario 2 showed a little reduction in cooling loads of 0.17 MWh per annum comparing with Scenario 1. Also, the total reduction in heating and cooling loads in Scenario 2 was less than Scenario 1 at a percentage of 11.14. In Scenario 3, the inclination was reversed than Scenario 2, aiming to soften the daylighting performance. By reversing the inclination, the solar gain was reduced than Scenario 2 and Scenario 1, which eventually led to a lower internal air temperature at 17.48 degrees Celsius. However, the daylight performance for Scenario 3 was enhanced in terms of illuminance and diversity, comparing to Scenario 2 and Scenario 1. On the other hand, Scenario 3 failed to reduce the annual heating loads in comparison with both of Scenario 1 and 2, with an increasement of 1.82% of the base case. As for the cooling loads, Scenario 3 achieved the highest reduction at 0.91 megawatt-hour per annum among the other scenarios. Overall, Scenario 3 came with the least reduction in the total annual heating and cooling load at 9.88%. In conclusion, the vertical sun space successfully achieved a balanced design in terms of heating load reduction and daylight performance. By contrast, Scenario 2 managed to reduce the heating load at highest value. However, this resulted in a lower reduction in cooling load and an intense daylighting performance. Finally, by reversing the inclination in Scenario 3, the daylighting performance was the most appropriate than the other scenarios, but this scenario was the least efficient in terms of energy performance.
Our third proposed scheme is a multimodal dynamic facade that responds to the climatic conditions throughout the year. This facade will be achieved through hourly calculations for cooling and heating loads for the three different modes. The first mode is called open plan, where two glazing sliding doors are mounted on the sides of the chalet. Hourly heating and cooling loads for this mode were simulated, and the lowest recorded values were selected for mode implementation, where this mode will be operating for 3,600 hours during 5 months throughout the year. After that, the glazing sliding doors moves toward the external glazing facade, leaving a 50 cm gap and forming the second mode of the double skin facade, where the outer air inlets and outlets are also opened. The double skin facade mode will be operating partially during 4 months, with a total number of 2,040 hours. Finally, the glazing sliding doors move towards the internal living area, and 4 windows are opened, creating the third mode of the sun space. The vertical sun space mode will be operating for 3 total months, and partially during 4 months for a total of 38 days. After determining the most suitable mode for each day, a smart system will be integrated within the design, where this system can automatically operate the facade configuration or even show the recommended mode for the users, and they can manually implement this mode by themselves. After assessing the dynamic facade energy performance, we found out that the heating loads were reduced by 11.71% than the base case. Moreover, the annual cooling loads were reduced by an amount of 0.82 megawatt-hour per annum, comparing with the base case. Finally, the total annual heating and cooling loads were reduced by 18.4%.
A comprehensive assessment was conducted in terms of heating and cooling loads between the base case and 3 proposed skins. Regarding the heating loads, the dynamic facade achieved the highest reduction, followed by the sun space at 11.71%. For the cooling load, double skin facade came as the best skin with a reduction of 0.9 megawatt-hour per annum, followed by the dynamic facade and the vertical sun space at a reduction of 0.83 and 0.42 megawatt-hour per annum respectively. Finally, for the total heating and cooling load, the dynamic facade achieved a remarkable reduction at 18.4%, followed by the sun space at 13.53% and the double skin facade at 9.88%. Based on the final assessment, The dynamic facade was found to be the most efficient skin design among the other, so it will be carried forward to the next level of design where an active design strategy will be integrated within it. The selected active design strategy is PV, as it is commonly used among the site. We use the total energy as an indicator to determine the amount of reduction after integrating the PVs. The dynamic facade with PV total energy dropped down to 17.42 megawatt-hour per annum, while the base case total energy is 23.86 megawatt-hour per annum, which means that total reduction of 27% was achieved.